Hello, I'm KSteinacker. I'm a student in ECE 312, 332, and 342. I'm going to be integrating the knowledge of those three subjects into discussion of the transmission line of. As discussed in the introduction to this video, we'll be talking about the transmission of a signal on a cell phone, and that'll be this whole part of the block diagram here. And now we're going to talk about taking a voice baseband signal, amplifying it, mixing it, filtering it, and putting it out through the three different courses discussed in the junior year for these KIs. And ECE 332, we're talking about these amplifiers and some of the circuitry that goes into this mixing circuit. And we're talking about local oscillator as well. And in 312, we're talking about some of the signal manipulation done with the mixer as well as with this filter. And in 342, we'll be focusing on the antenna. We can now start talking about the baseband signal that we start with. It's going to be a voice signal, so it's going to be somewhat band limited to about 20 kilohertz. So we have a current source set up here. Our voltage gain is going to be GM times R naught. This is GM, then naught, so GM naught. And R naught's the output resistance. So we're going to have some kind of load. When we think about output resistance, it's going to be the output resistance of this transistor and the output resistance of this one, because we're looking into the drain to find the output resistance for both of those. Conditioning, is we need to condition this, is going to raise it to a higher DC value, larger bias, so this is 0.3 volts. Let's say go to 0.6 volts. That conditions the signal to go into the mixer. And lastly, it filters out noise. We've conditioned our signal, amplified our signal, and filtered our signal at this preamp, and this is going to be going into this mixer, which has a multiplication that it does with a carrier signal. This is how the signal is coded. It uses the high frequency carrier and it codes our data, our voice signal, using amplitude modulation. This is you can see our original signal is actually coded with these various amplitudes of the high frequency carrier. The United States, we have what are here highlighted in yellow, these two different GSM bands. So 900 to 1.8 gigahertz, 900 megahertz to 9.8 or 1.8 gigahertz. We could look at CDMA, and I see up here where we have most of our routers and everything is in this like 2.4 gigahertz range. Now, as we have talked about, we have to take this conditioned voice signal and we have to multiply it with a high frequency carrier signal, and we do that with this mixer. Very rudimentarily speaking, we have a basic schematic of a mixer where you have the baseband voice signal, the local oscillator, they mix together and you get something like an amplitude modulation signal. We're looking at, we have the magnitude 1 of j omega is referring to the baseband signal. It's centered around this axis. It's band limited to band omega b. We have our local oscillator signal, cosine omega naught t. We know that the frequency response for the Fourier transform is deltas at omega naught. We're going to say the omega naught's about 2 pi times 910 megahertz. Multiply these two signals together, we're going to get copies made at omega naughts. So I got a 20 kilohertz plus or minus band around 910 megahertz. At this point, we have already gone through the preamp and mixed our baseband signal with the carrier power amp. And this speaks how it contributes to linearity and power efficiency, and that goes to the input of a bandpass filter. Here's the Bode plot for a bandpass filter. The idea behind the bandpass filter is that it has large attenuation for small frequencies. The small frequencies get attenuated at minus 40 and minus 60 dB here, and also large frequencies get attenuated. And you select a band of frequencies you actually want to pass. And a way of attaining this bandpass filter property is by taking a low pass and a high pass filter and then combining their properties in series. Here's a sketch of a low pass. Here we have the passes, frequencies up until omega naught, or the Fourier transform of a high pass filter. And you can see that the low frequencies do not have any magnitude, but higher frequencies do. Now if you take those two and you combine them, if you multiply the Fourier transforms of the two together, you get this band pass filter. Filters below this omega naught, omega 1, and it filters above this omega naught, but it passes the frequencies in between. Now that we've completed our signal trip all the way through the bandpass filter, we're ready to send our signal to an antenna. A cellular phone antenna can either be integrated into the circuitry of the phone, as shown here, or it can be integrated into the case of the phone. In any case, there's many considerations for how to properly transmit the electromagnetic signal that we're dealing with. An antenna needs to be on the same order of magnitude of size as the wavelength of the electromagnetic wave. We have a frequency of 2.4 gigahertz, CDMA technology, order of size. For sending and receiving 2.4 gigahertz, we're going to need to have something in that order of size in order to decode that code standard. I hope this video was clear and informative, and I'll see you next time for knowledge.